Okay, welcome back. So on this tab, we're going to look at food delivery checkout. The Campus Food Delivery app redesigned its checkout flow. To see if the new flow changes the average time to place an order, 60 students were randomly assigned to use either the old checkout or the new checkout. Times and seconds to complete an identical mock order were recorded. Alpha is 5%. So which is the correct test? It's going to be a two-sample t-test, otherwise known as an independent samples. And as I mentioned before, it's independent because it's two different groups of students. It's not the same group measured twice, which would be paired. We are testing the difference in sample means. Thus, we'll be using the sampling distribution of sample mean differences, probably should be bold-faced, delta x bar, which is a t-distribution. So it's the difference in two sample means, mu1 and mu2. This is a two-sample test, which compares two samples to see the likelihood that they belong to the same population. By convention, the mean of the comparing group is x1, x bar 1, which sample is the comparing group. So we have comparing, which is new, x bar 1, which is new, so that's new. And the reference group is old. The null hypothesis is that they have the same population mean. And what's the alternative in this case? It says just changes the time. We're not predicting a direction. And that means that it's a two-tailed test. Okay. So x bar new is average. And x bar old is average. And count of new and count of old. And standard deviation dot s of new. Remember, we're doing this standard deviation because we don't have the population. Standard deviation is not known. And so our standard error is going to be, as you see here, the square root, effectively the average of those two standard deviations divided, each one divided by their sample size. So that squared divided by n1 plus this one squared divided by n2. You're probably wondering, why do we have to square it? Because we're taking the square root. So square it and take the square root. You're kind of right back where you started. But this time after you've done the division. Okay. By the way, if you're ever wondering why is it called standard error as opposed to just error, because it's effectively standardized. How is it standardized? By dividing by effectively the square root of the sample size. Okay. Alpha is 5%. And the probability, we're going to divide alpha by 2 for each of these, since it's a two-tailed test. And then do t dot inverse. Start out with an equal sign might help. Probability and the degrees of freedom, which again we're not making you calculate. Though this time is kind of curious, because the sample sizes are both the same length. Notice how the degrees of freedom actually is n1 plus n2, right, divided minus 2. Whereas in the one of our other examples, sample sizes were different, and you couldn't do it quite that simply. Equals t dot inverse. Remember, for the right-hand side, it's 1 minus the probability, degrees of freedom, and then the critical value is just the t-score times the standard error. Same for this one. So now we've got our critical cutoffs. All right, what is our delta x bar? Going to be u minus old. All right, so that's negative 4.38. Where might that fall? It's going to fall obviously in here, so it's going to be a reject. But let's go ahead and play this out. T-score is equal to that difference divided by the standard error. So that places it, and then the probability is t dot dist t-score, degrees of freedom, and true. So very low probability, an extreme t-score, reject the null. All right, margin of error. And remember, for margin of error, we can use the right-hand side t-score of a two-tailed test. So it's just going to be equal to that times the standard error. And then we'll go ahead and construct the confidence interval. Plus the margin of error, and on the other side, delta x bar minus the standard error. And as you can see, the confidence interval does not cross the 0 point, which means that, again, it's going to be a reject. So we're getting all these indications of why this is reject. All right. Our alpha that we're using is the 2.5. P-value that we calculated is 0.86%, which is less than alpha, and that's going to mean we reject. So now we use the critical value approach, the lower critical value, and this time we want the t-score. That one, the upper one is that one, test statistic is that, which is more extreme than the lower one. So, and you can see that here, t-score more extreme than the lower t-score. So we're in the rejection area. So we reject the null. So because we're rejecting, we think, getting back to the problem itself, this is about time to place an order. So it's less time, right? So mu u is significantly less than mu old. and that's statistically significant. Our standard error, our sampling error, 1.79. And 95% empirical rule would be from negative 3.57 to 3.57. And the raw cutoff is over here. It's going to be on the negative end. Raw value. And our actual sample difference is there, which exceeds the cutoff. And we're estimating mu nu minus mu old. And we're 95% confident that the population mean difference is between negative 7.96 and 0.81. How do we get that? Negative 7.96, negative 0.81. And that takes care of this one. Okay, pizza. A local food lab in Athens, Ohio, runs a blind taste test of 2 pizza shops, Goodfellas and Avalanche. Each participant samples 1 slice, randomly assigned brand, waits 5 minutes, then rates on a slice on a 0 to 100 taste scale. The dataset contains 24 Goodfellas ratings and 24 Avalanche ratings. Using a 5% significance level to decide whether the pizza brand changes the average taste score. In other words, are they coming out the same? Or is the difference, obviously there's going to be some difference. Is it a significant difference? So independent samples t-test, two sample t-test. It's the difference in the population means that belong to those 2 samples. That's how we get the delta X bar, because it's difference. And who is the comparing group? Comparing group here is Avalanche. The reference group is Goodfellas. So these are arbitrarily assigned for the purposes of this problem. One isn't, sort of by definition, the reference group. So comparing is Avalanche. Reference is Goodfellas. Null hypothesis is that they're the same. Alternative is that they're different. So that makes it two-tailed. Okay, so equals average Avalanche equals average Goodfellas. If I could spell it, would help. Equals count Avalanche equals count Goodfellas equals standard deviation dot S of Avalanche and equals standard deviation dot S for Goodfellas. The standard error is the square root of this square divided by that plus S2 squared divided by N2. Alpha is 5%. So we'll split alpha and then use T dot inverse start with an equal sign. Pick up the degree. degrees of freedom. You notice this degrees of freedom also worked. It's just n1 plus n2 minus 2 because they're the same length. Samples have the same count, in other words. Okay, and then this is t dot inverse. This time it's 1 minus probability, since we're looking right, degrees of freedom, and delta x bar, critical value, the raw critical value is simply going to be the t-score times the standard error, and same here. Okay, delta x bar is going to be that minus that. How did I note it? It's comparing minus reference. That's just a convention. And the t-score equals t dot dist. Oh, sorry. My bad. The t-score equals the delta x bar divided by the standard error. Probability is equal to t dot dist x degrees of freedom untrue. The margin of error, remember we are allowed to use the right hand two-tailed test, or if you didn't have that, you could look at the formula there, times the standard error. Delta x bar, and we say equals that plus what? Margin of error equals that minus margin of error. And you can see that the margin of error crosses 0. So this is going to end up being a fail to reject. You can also see it's going to be a fail to reject here because the test statistic lands here outside of the rejection area. And we can also see it's going to be a fail to reject because the probability out here is 4.8%, but we only had on each tail 2.5% to play with. So lots of indicators that this is failed to reject. And failed to reject in real terms means the taste testers couldn't tell the difference between on a 100-point scale. In other words, if you look at these numbers, 80 and 84, it means that on a 100-point scale with 60 participants, that's not a big enough difference that you could actually say Goodfellas is better. The difference would have to be bigger for you to reach that conclusion. Alright. So alpha p-value is there. P-value is bigger than alpha, so fail to reject. And the lower critical value was negative 2.01, which is this cell. The upper one is 2.01. The test statistic t-score is so fail to reject area, fail to reject the double. And so there's not a significant difference, which means their tastes are equal, or equally good, I should say. And so the difference is statistically not significant. And the sampling error is pretty high. And by the way, the sampling error being pretty high explains why that wasn't a big enough difference. If sampling error had been really low, then what that difference would have been. All right. And that might just be a result of too much variability in the samples. Okay, so let's look at the 95% confidence interval from negative 4.32 to 4.32. And the lower cutoff is going to be and this is the raw value. Our actual sample mean difference was way over here. And what are we estimating? Oops. Sorry. What are we estimating with the confidence interval? I guess I shouldn't have put an equal sign. So we're estimating the difference between the two population means, and our interpretation is that, I think those are the right values, yeah, from negative 8.02 to 0.68. Negative 8.02 to 0.068. So it looks like we're good to go.